our hodgepodge unit, we're going to be looking at how we can apply our derivative or differential equations without integration. So how can we look at the original function without actually integrating? And so that our first thing that we're going to be looking at is what we call our slope fields. And so to solve most of our differential equations, so equations that have relate variables with their derivatives, so a standard one would be something like, dy over dx is equal to, say, 4x squared y or something like that. We would need to separate the variables, right? So that would be our step, and then we would integrate both sides. But sometimes, as we have experienced, integrating those can be very challenging. And so one of the things that we can do is we can take a graphical approach. And when we do that, we are going to be looking at each point, xy, in the xy plane, where our function is defined by the slopes given of that derivative equation. So we will be looking at that. So we will be drawing a short line segment that will be representative of our tangent line, but we'll be looking at just only a small portion of it. And that line segment will represent the slope of each of those tangent lines at certain points, so we won't have to do it everywhere, and given in a particular domain of our function. And so each line segment that we draw, so each of those short line segments that we draw, it has the same exact slope as the curve itself through that point of tangency. And so a slope field shows the general shape of all the solutions. And so what that means, we know that if we were given, say, the derivative is equal to x. So if I were to integrate that, right, I would get y is equal to x squared over 2 and then plus some constant. So if I were to look at x squared over 2 plus some constant, I know x squared over 2 is some sort of, parabola, right? So it would look something like that. But then that plus c then allows it to be, a parabola pushed up or a parabola pushed down. So this would actually have three solutions, right? y1, y2, y3 of infinitely many, because I can slide up and down all that. So that's why we see the general shape of all the solutions. And so what would happen is we would just be looking at, what would be the slope at that point? It would be something like that. What would be the slope at that point, right? So we're just going to be looking at just those slope pieces and not the whole function, because what if we couldn't integrate? Okay, so then another component, so a slope field has other names. So a slope field can also be called a directional field or a vector field. And so it is just a sampling of short line segments with particular slopes. Okay, so let's go ahead and actually do a problem. So they're going to ask you to do a variety of things in your homework or in practice in class, I should say that tomorrow, or on an exam. One of them is to actually sketch a slope field. And so they will give us restrictions here. So if our derivative is x minus y, so that's beyond our ability to integrate, like we don't know how to integrate that. And this is saying that x is an element of the values from -2 to 2. So we are looking on the x-axis from -2 to +2, and we'll only be graphing the integers. And then y is an element from -1 to 2. So on the y-axis, we're only looking from -1 to +2. And so lots of different ways to do this problem, but the most common way is that we would just set up a t-table to figure out, like what are each of those values. So we would have x and y. And then we would have the slope of that line. So the slope of that line would be our dy dx, which is x minus y, right? So dy dx, so we're going to evaluate our slope at each of these ordered pairs. So where all these pluses are located, plus anything that lands on the axes. So I'm just going to start right here at 0, 0. So if x were 0 and y were 0, I would get 0 minus 0. And so I would have to draw, a slope that is 0. And we're just doing a short line segment. Let me actually erase that dot I put there. So a short line segment that has a slope of 0. So at the ordered pair 0, 0, I would draw a horizontal line. So then let's go ahead and do another one. So let's do the ordered pair up above here. So over 0, up 1. So x is 0 and y is 1. So 0 minus 1 is negative 1. So at this ordered pair, 0, 1, I would draw a line segment that has a slope of what I call negative 1. So something that looks like that. Okay, so let's keep moving up the line. So let's go over 0, up 2. So 0 minus 2, that would be negative 2. So then this would also have a negative slope, but it would be a little bit steeper, right? Because negative 2 is steeper than negative 1, so something like that. And then let's do just a few more so you can get the gist of what we're doing here. So let's do, how about the ordered pair over here? So that would be over 1, 0. So 1 minus 0 would be a slope of 1. So over here, so a slope of 1. So I'd have a positive slope, but I'm just winging it. So it doesn't have to be precise. And then let's do, how about 2, 0? So that would be 2 minus 0, so a slope of 2, so a little bit steeper than the one I just drew, so maybe something like that. And then let's do a negative just for fun, so let's do this one down here. So 1, negative 1, so that would be 1 minus negative 1 for a slope of 2. So I would try to make it mirror that one, but it doesn't need to be precise. And then I have that random line there. And so that's how I would sketch a slope field. Okay, so we're not going to graph all of them, right? But we would do that. And so when we have all of those graphs or all those tangent line slopes graphed, like we would get a bunch of short little line segments, all of which would represent that differential equations slope field. Okay. All right, so one of the things that we're going to have to be able to do is like we look at a slope field and have to maybe answer questions to that. And so our examples here of A and B, this is a picture of a whole lot of slope fields that, or a whole lot of pieces that were graphed in a slope field. And so if you look at this, like you can see like trends in this data, and that's what we're looking for. So to determine the differential equations being graphed in the slope field, we're going to have to look for trends of the slope. Like what are some commonalities that we see? So things that we should be looking for is there sections where we have positive slopes versus negative slopes in the different quadrants. You know, so like if I look here in quadrant 1, what do I notice about all of those slopes? All of those slopes are positive in quadrant 1. So that would be something to take note of, right? So when X and Y are both positive, I generate positive slopes. If I look over here in quadrant 2, what am I noticing? All of the slopes are negative, right? And then if I look in here, hey, look at those. All of those slopes are negative. So that would be something that we would be searching for, right? So in general, every slope that's in this quadrant is positive, over here negative, and over here positive. And so that would be like trends I'm looking for. So I don't have quadrants identified in this one, but that's all right. So the other thing that we would be searching for is, do we have any section of the slopes that are either 0 or undefined? So horizontal would be 0, right? Vertical slopes would be undefined. So if I look right here, so it looks like all my slopes are 0 on that particular line, right? So if I look in this section, those are all looking horizontal. Let's see, what else do we have? So here, I'm guessing on the y-axis, I would be horizontal because I go from a negative to a positive. So that must be that I must have a bunch of slopes of equaling 0 on the y-axis. And then not quite vertical as I move over here to the right. Like they're pretty steep, but I would say they certainly don't look vertical. Okay, so I'm looking for like, you know, so when I'm studying or analyzing a slope field, like that's what I'm looking for. Okay, so then the other section, the other piece that we have to look for, and this is probably one of our most important one, is do we have any slopes that are running parallel to each other? Okay, so meaning like vertically or horizontally, are they running parallel to each other? So if I look at this right here, every slope right here is running the same, right? And that is true all the way down. Like it doesn't matter which horizontal line I look at, I see that all of those slopes are running the same. And then if I look at this one, all of these are running vertically. They're all running parallel to each other, right? So it doesn't matter where I am in that highlighted line, all of those slopes look exactly the same. And that is one of those pieces that we will be actually probably using more than any, right? So if I look at this graph right here on that vertical line, the slopes are all parallel. If I look at example B, so if I'm looking at the horizontal line, the slopes are running parallel. And so that actually tells us quite a bit. So if I look right here, so if this were at, so like, I don't know where this is at, but let's say this is at x is equal to 5. So when x is equal to 5, it doesn't matter what y is, right? Y could be 1, it could be 12. It doesn't matter. They all have the same slope at x is equal to 5. So what that means is that the slope is dependent on x. That it's not going to be in terms of y, it doesn't matter what y is. So when I look at this right here, dy dx would be in terms of x. Because at x is equal to 5, that determines the slope. It doesn't matter if you are at y1, because the ordered pair here, 5, 1, generates the same slope as if I was at 5, 5. And so if they're running vertical, then this is what it's telling me. And then over here, if I look at dy over dx, so if I look at, again, I'm just going to randomly call these. So like, let's say this was at, x is equal to 2. I have all different slopes, right? But if I were on, so let me put in an xy axis. Let's pretend that's my xy, since I failed to do that in the drawing. Okay, that will help me explain it just a little better. So if I look right here, so if this is at y equals 1, y equals 2, all of the slopes are the same at y equals 2. So it doesn't matter if I'm at the ordered pair 2, 1, or if I'm over here at the ordered pair 2, 2, how about 1? Let's call that 1, and we'll call this 4. So when x is 1, the slope is the same as when x is equal to 4, because it is dependent upon what y is. So when my dy over dx would be in terms of y only. So this would be y terms only. Okay, so it depends upon where you are on the y-axis, right? Where am I on the y-axis? So where am I on the y-axis? That gives me my slope. And then over here on my example A, where am I on the x-axis? So where am I on the x-axis? That determines my slope. All right, so let's go ahead and let's take a look at this example here. And so we're looking to match our slope fields. So we're going to look for trends. So the first thing I always look for is, do I see anything like horizontally or vertically all the same? So I see here, these are all slopes that are horizontal, right? So they are all parallel to each other. And then the same here, right? So these are all parallel to each other. So that's going to be my first little look. But I don't see that on A, no parallelness, and nothing on D either. Okay, so what that means is, so let's take a look at this. So I have my slope over here, depending upon where I am on the y-axis, right? Where I am on the y-axis, that gives me parallel values. So this has to be in terms of y only. So the only one up here that is in terms of y only is this one here, right? Because this has an x in it. This has both an x and a y, and both an x and a y. So then number 2 must be C. And then if I look over here at B, it depends on where I am on the x-axis, right? Where I am on the x-axis. And so this would have to be in terms of x, right? Doesn't matter where I am on the y, it matters where I am on the x. So then the only one in terms of x only is this one right here, because this one again has both an x and a y, both an x and a y. So then that means that 1 is number B. So then now I'm down to 3 and 4, right? So that's either A or it's D. So then now I'm going to look at positives and negatives to see if that helps me. So over here, I can see in quadrant 1, these are all positive. In quadrant 4, these all look negative, and then this is a mixture and a mixture. So over here, these are all negative, all positive, all negative, all positive. Okay, so this one, so I'm going to kind of attack this one here first. All right, so let's see. So when I do x divided by y, and then the opposite of that. So let's check quadrant 1. So in quadrant 1, x and y are both positive. So when I divide a positive by a positive, but then don't forget I have the negative, so that would make that all negative. So that works. And then over here in quadrant 2, my x values are negative, my y values are positive. So then when I do a positive divided by, whoops, let me start that over again. Okay, so my x is negative divided by a positive. That would give me a negative answer, but then I'm doing the opposite of that. So that would be positive. So I think that must be true all the way around. So then I'm going to say that this is number 3. And by elimination, then 4 must be A. But I'm still going to check it. So if I add 2 positive numbers together, then I will get a positive, so that works. And then these are all saying that the slopes are 0 on the y equals x line, which is totally true, right? So on the y equals negative x line. So like at this ordered pair, for example, that's 1 comma negative 1. And if I add those together, I get a slope of 0. So that's why I have all those. Okay. All right. And so that's how I kind of analyze those graphs. All right, so let's take a look at example 4 here. So they want you to determine the sign of y prime at the ordered pair 4 comma negative 3. So 1, 4, I think that's right here. Let me double check that. 1, 2, 3, 4, 1, 2, 3. So what is the sign of the slope at y prime? So that is the slope here, and that is a negative. So on the same axis as the slope field, we want to sketch a solution curve of the differential equation that passes through the ordered pair 2, 0. So let me erase this one. So at 2, 0, so that would be right here. So what that means when they ask us for a solution curve is that all of these lines right here represents some sort of point of tangency on the graph. And so what we're trying to do is kind of follow along those lines. So what we're doing is we're saying, okay, what does this slope look like? So that is a positive slope. That means it's going to force the graph to go up and to the right, up and to the right. So all I'm going to do is just kind of follow along. I'm not trying to go dot to dot. I'm just trying to follow along what those slopes are telling me the graph is doing. It's showing that it's increasing but leveling out, right? So increasing but leveling out, so concave down. And then I'm going to kind of follow along the same way here. So then I'm going to go downwards and to the left. Again, we're not playing dot to dot. We're just trying to kind of follow what those, kind of force field is doing. What is that kind of indicating? And so that would be a solution curve. When we just take a point, it doesn't matter where that point is, and we just kind of follow the trend of the slopes. What are the slopes telling me to do? And so like that would be another example. Okay, but that's not through 2, 0. All right, and then let's take a look at this one here. So this is saying that consider the differential equation dy over dx is equal to y minus 1 over x squared, where x, of course, cannot equal 0. And then we want to sketch the slope field for the differential equation at the 9 points that are indicated, so wherever those dots are. So then, again, we're just going to do the same thing again. So I'm going to set up an x and a y. So my first order pair is over here, so that would be at 1, 0. So that would be negative 1 over 1. So that would be a slope of negative 1. So say something like that. And then let's do 2, 0. So that would be 0 minus 1 over 2 squared, so negative 1/4. So that would be a negative slope, pretty flat. So we'll say something like that. And then let's move up. So at 1, 1, so that would be at, oops, uh-oh. Hold on, what's happening here? Okay, so let me try that again. Maybe, there we go. So that would be 0. So that would be just a flat. So in fact, everywhere y is equal to 1, I would get 0. So wherever y is equal to 1, that's pretty nice. So I would get 0 everywhere. And then let's go ahead and let's do this dot here. So -1, 0. So that would be -1 over 1. So that would be -1. And then we have these 3 dots left here. So we'll go over 1 up 2. So that would be 1 over 1. So that would be a positive slope of 1. And then we would have 2, 2. So that would be 2 minus 1 is 1/4. So positive 1/4. So a flat graph. And then our last one, so -1, 2. So that would be 1 over 1, so positive 1. So something like that. Okay. All right. And then let's take a look at what is happening. I think I might have froze my screen. Well, I don't know. Sorry. There we go. Okay, I was frozen there. Okay, so then now for this last part. Okay, so we want to solve the differential equation. So this is a review off of chapter 5. So this was quite a while ago. So they're asking us to solve this equation. And so in order to do that, the first thing we want to do is always to separate our variables. So that's going to be our first step. So I'm going to go ahead and multiply both sides by dx. So this again is from chapter 5. So we'll see how we fare. And then I'm going to divide the y minus 1 over to the other side. Okay, so separate our variables. That's our first step. So let me write the steps off to the side here. And then once we do that, we want to integrate both sides. And then I'm just going to do a rewrite here just to make it easier for me. So on the right side, I can do power rule. So I'm going to add 1 and then divide, and there'll be some sort of constant. Over here, I can't do power rule, right? Because that would give me 0 divided by 0, but that is a natural log. So I'm going to squeeze in that natural log there. So then now I have an initial condition of 2, 0. So I can evaluate that now, right now, if I wanted to solve for C, or I can do it later and solve for y first. But I'm going to go ahead and solve. So I'm going to exponentiate both sides. So then I would get the absolute value of y minus 1. And then this would be e to the negative 1 over x plus c. But again, I can pull that apart. So that would be -1 and then e to the c. So this is like from a while ago, right? So we're integrating and then we're solving. And e to the c is just another value of c. And then I'm going to let x equal 2 and y equals 0. So the absolute value, I'm sorry, I'm trying to do this in my head and I should be writing this out. Okay, so then that would be CE to the negative 1/2. So that would be absolute value of -1 would be 1. And then I am going to divide by e to the negative 1/2. And so then that would just be C is equal to just e to the 1/2, right? Because if I pull that up to the top. Okay, so then I have that equation. So I've lost track of where I was at. So let me see, where is my, right there. So I have the absolute value of y minus 1 is equal to C, which was e to the 1/2. times e to the negative 1 over x. And then it does ask me for y as a function of x. So I would have y equals 1 and then plus e to the, add my powers together. So what is that? 1/2 minus 1 over x. I did that kind of quickly. I hope I didn't make a mistake somewhere. So if I did, be sure to shoot me a message. Okay, so that is the end of